Let's discuss general graphing guidelines. So if we want to make an accurate graph of a function y equals f of x, we need to determine all of the following. First of all, we need to find the domain of the function. Most likely the domain of the function will be exactly the intervals of continuity, but situation could be different. So that's the first item. Then secondly, we need to talk about x and y intercepts. Those are easy to find. Then we need to test for possible symmetry of the graph. If the function is even, then the graph is symmetric with respect to y-axis, and if the function is odd, then the graph is symmetric with respect to origin. Then we need to find any vertical asymptotes. Those usually come from the zeros of denominator, especially, well, those should be in the places where denominator is 0 and numerator is not 0. Then we use third derivative to investigate for any critical points where derivative is 0 or does not exist, and we use third derivative to determine where function is increasing or decreasing, and to find relative extrema, relative maximum, and relative minimum. Then we use second derivative to find any points that are suspicious for being points of inflection. And then we use second derivative to find the intervals where the function is concave up or concave down, and to successfully determine where we have points of inflection. And for the last item, we discuss limits at infinity. So those determine the end behavior of the graph. If the limit as x approaches positive infinity or negative infinity is a finite number, that's usually called the horizontal asymptote. Or if the limit as x approaches positive or negative infinity happens to be infinite, that's also a useful information. Let's work on one example of finding the graph of some function. So we consider this function f of x being 2 times x squared minus 9 over x squared minus 4. For the first item, we determine the domain of this function. And we notice that the function is not defined when denominator is exactly 0. So we solve equation x squared minus 4 equals 0, that gives us x equals 2 and x equals negative 2. So the domain of this function is easily the interval from negative infinity to negative 2, an interval from negative 2 to positive 2, and interval from 2 to positive infinity. Those happen to be the intervals of continuity as well. For the second item, we find x and y intercepts. So to find x-intercepts, we set the function itself equal to 0 and solve. So the fraction being 0 is equivalent to the numerator being 0, which gives us x squared equals 9, which works out to be x equals positive or negative 3. So those are x-intercepts. Likewise, to find y-intercept is much easier. We set x equals 0 into the function and find the value. So put x equals 0 into the formula and you'll get 18 divided by 4, which is 9/2, or in decimals that would be 4.5. And then for the third item, we test for some possible symmetry of this function. So we replace x with negative x in the formula for f of x and simplify. We see that f of negative x is twice the negative x squared minus 9 over negative x squared minus 4. And since negative x squared is equal to exactly x squared, because negative 1 squared is 1, we see that f of negative x simplifies to exactly the same expression as f of x. And that actually implies that this is an even function. And that is really nice for us, because a graph of an even function is symmetric with respect to y-axis. For the fourth item, we look for any vertical asymptotes, and we see that if x is -2 or +2, denominator is 0 and numerator is not 0, and that makes those two x values to be vertical asymptotes. For the next item, we work on finding the derivative, so f prime will be the derivative of this whole expression, and we use quotient rule. This is derivative of numerator times denominator minus numerator times derivative of denominator, all of that over denominator squared. And we will get derivative of 2x squared is 4x, x squared minus 4 is from there, and then derivative of x squared is 2x, and 2 times x squared minus 9 is still there. Then we will distribute 4x over x squared minus 4 and get 4x cubed minus 16x. And then remove the parentheses here and we get negative 4x cubed plus 36x. Then combine all the like terms and we arrive at 20x over x squared minus 4 squared. That's nice. Once we have the formula for the derivative, we note that this derivative is not defined at exactly the same places as the original function, x equals positive or -2, and on top of that there are some places where derivative is 0, so set the formula for the derivative equal to 0, that makes the numerator being 0, and that results in x equals 0. This is pretty much the only critical point. Because, well, even though derivative is not defined at positive or -2, the original function were not defined there as well. That's why those 2 points are not critical points. On to the next step. Now that we have the formula for the derivative, we work on finding intervals where f of x increases or decreases. So we set up all those intervals, the interval from -infinity to -2, interval from -2 to 0, interval from 0 to 2, and the interval from 2 to positive infinity. We choose test point at each of those intervals, -3, -1, +1, +3, and test what happens to the derivative everywhere. And we see that at -3 derivative is negative. Let me actually copy the value of the derivative so that it's easier to see. So the derivative was 20x over x squared minus 4 squared. Now you can easily see that if you put x equals -3, and here denominator is positive and numerator is negative. Likewise at -1, numerator is negative, denominator is positive. Then derivative is not defined at -2. At 0, derivative is exactly 0. That's a critical point. At 1, derivative is positive. At 3, derivative is positive as well. What it makes the function do, the function is decreasing whenever the derivative is negative. The function is increasing whenever derivative is positive. And here the function switches from decreasing to increasing. This makes f of 0 to be relative minimum. So again, let me put the third derivative next to the function. So we find the second derivative now. That's the derivative of 20x over x squared minus 4 squared. By the quotient rule, that's the derivative of numerator times denominator minus numerator times derivative of denominator over x squared minus 4 to the 4th power. So we work out the derivatives. Derivative of 20x is 20. Derivative of x squared minus 4 squared is, by the chain rule, 2 times x squared minus 4 times 2x. Then we factor out x squared minus 4 in numerator, and we see that there is 20 times x squared minus 4 left, and negative 20x minus times 2 times 2x left out of the next term. Once we factor this stuff out, we can cancel x squared minus 4, and arrive at this expression: 20x squared minus 80 minus 80x squared. This simplifies to negative 80 minus 60x squared, and then we take negative 20 out, and that's the formula for second derivative. What we see that the second derivative is not defined at exactly the same places as the first derivative and the original function were not defined. And the second derivative is actually never zero, because equation negative 20 times 3x squared plus 4 is actually, this one has no solutions. So now we're gonna use the second derivative. Let me actually copy it. So here we're gonna need second derivative. So f double prime of x was negative 20 times 3x squared plus 4 and divided by x squared minus 4 to the third power. So we use the second derivative to investigate what does the function do. There are essentially three intervals for us to focus on: negative infinity, negative 2, from negative 2 to positive 2, and from 2 to positive infinity. On each of those intervals we choose those test points, negative 3, 0, and 3, and then put those test points into the second derivative. So you see what happens at negative 3. We put negative 3 in, and the numerator will always be negative, because 3x squared plus 4 is always positive, and negative 20 times that is a negative number. And then x squared becomes 9, minus 4 is positive 5, so we get negative numerator and positive denominator here, hence the whole result is negative. At 0 we're gonna get negative 20 times 4 divided by negative 4 cubed, all of that works out to be positive. And likewise at x equals 3 we get a similar picture, we get a negative result. So it tells us that the function itself is concave down on the first interval, concave up on the second, and concave down on the third. There are no points of inflection because the function is not defined at negative 2 and at positive 2, even though the concavity changes. Then on to the last step, we consider limits at infinity and behavior of this function. So limit as x goes to positive infinity of the original function is a limit of the same expression when we distribute 2. And then we're going to take out x squared, so that we have x squared times 2 minus 18 over x squared, and x squared times 1 minus 4 over x squared here. How does it help? Well, it helps us cancel x squared to begin with. And then, as soon as we have this, 18 over x squared actually goes to 0 as x goes to infinity, and 4 over x squared actually goes to 0 as x goes to infinity. So the end result is positive 2. It tells us that y equals 2 is a horizontal asymptote. Likewise, as x approaches negative infinity, we can do the same algebraic steps up to the next to the last step. And here, again, as x goes to negative infinity, 18 over x squared approaches 0, and 4 over x squared approaches 0. It's a fixed number divided by something huge. It works out to be as good as 0. So this is again 2. So on both ends, the graph of the function will approach y equals 2. That happens to be the horizontal asymptote. So that's what this line claims. So we see that y equals 2 is a horizontal asymptote of the graph. Now it's the time to put all the information together. So we are working on graphing this function, and let me put all that we know about first and second derivative on this number line. So there are points -2, 0, and +2. So this is the x-axis. And let's see what happens on each of those subintervals. So -2 and +2 are vertical asymptotes, so I'm putting those dash lines for the vertical asymptotes. On the interval to the left of -2, both first and second derivative were negative. So the function itself must be decreasing and concave down. And that makes it look like this piece of the curve, so it must be decreasing and concave down. Likewise, between -2 and 0, second derivative is positive, third derivative negative, so the function should be concave up and decreasing. And that makes it into this piece of the graph, so it should be concave up but decreasing, so it's the left side of U-shape. Then between 0 and +2, both second and third derivative are positive, so it should be concave up and increasing function. That would be the other half of the U-shape. And to the right of 2, second derivative is negative and the third derivative is positive. So the function is concave down and increasing. That makes it into the left side of the upside down U-shape. Okay, now if we put all of that together on a single graph, we'll start to see the following picture. So here is the set of axes. Then we can put the y-intercept 9/2 and x-intercepts -3 and 3. Then there are vertical asymptotes at -2 and 2. And there is a horizontal asymptote at y = 2. And then, remember, to the left of -2, the graph should be concave down and decreasing. So it looks like this is the only way for it to be. And it has to go through -3. So that's the piece of the graph that makes sense in this case. And then between 0 and -2, the graph should be concave up and decreasing, so it's going to be going like this. And then to the right of 2 is going to be concave up and increasing, so this 9/2 is the relative minimum point. And then to the right of 2, the graph is increasing and concave down, so that's the only way for it to go, because it should approach y = 2, this horizontal asymptote. So this line is y = 2, horizontal asymptote, and this whole graph is y = f of x.